This screencast presents a qualitative overview of fluorescence anisotropy, trying to avoid the math as much as possible. It starts with a slide that's going to summarize the major themes, the big things that you'd ideally remember, both for the exam in this course and thereafter as you move onward in research careers if you do that. Fluorescence anisotropy essentially measures the relative polarization of emitted fluorescence versus exciting light. And so the two panels over here pretty much explain this. This panel shows the experimental, one typical experimental setup for this. When you polarize the light, in unpolarized light, the electric field has more or less a random orientation. When you polarize the light, well, as we'll see in the circular dichroism spectra section, you can actually produce light with a circular polarization, but anisotropy measurements are made with light with a linear polarization. So you pass the light through a filter that effectively constrains the electric field to point in one direction. The way it's schematized here, the electric field vector and the exciting light is pointing vertically along this page. And so then the light comes in with the vertical electric field polarization comes in this direction to a cuvette, where it will excite fluorophores in the cuvette, and then they will emit light. When the light is emitted, it will come out at all angles. It actually does not come out at all angles equally, but we won't get into that level of detail in this course. But in any event, the light emitted in this direction and in that direction is essentially equivalent by symmetry, right? If the exciting light is coming in this way and the light is linearly polarized, any kind of emission in that direction is symmetrical and should be equivalent to any emission in that direction. So the way the experiment works then is that a polarizer with one orientation, polarizer with an orientation parallel to the excitation polarization is put onto one of these two channels. This is a so-called T-format fluorescence anisotropy measurement geometry. And so in the two symmetrically equivalent directions, in one of them you put on a polarizer that is parallel to the direction of the exciting light, and the other one you put on a polarizer perpendicular to the direction of the exciting light. The G factor is an experimental correction you have to do to deal with differences in effectively the sensitivity and sort of, anyway, polarization artifacts and sensitivity differences between the two channels. This is a technical thing you don't have to worry about. If you're doing an anisotropy experiment, you'd have to worry about it for the purposes at hand. We don't need to worry about it. Okay, and so again, anisotropy then is going to measure the relative polarization of the emitted fluorescence versus the exciting light. So one channel will basically measure the emitted fluorescence that's polarized like the exciting light, and the other channel will measure the emitted fluorescence that's polarized perpendicular to the exciting light. Anisotropy will then be calculated as the intensity in the parallel direction minus the intensity in the perpendicular direction. So basically the difference between these two channels divided by the intensity of the parallel direction plus 2 times the intensity in the vertical direction. So a later slide will explain that. This slide is just trying to sort of get the highlights in the overview. And so now if we look at what's going on from the perspective of the fluorophores, this is, I'd say, possibly the crudest schematic in all of Lacowitz, but it sort of barely communicates the essential points, I guess. So this is now supposed to schematize the polarized light coming into a population of fluorophores. We'll talk later about the fact that the polarized light will preferentially excite fluorophores with their transition dipole moments aligned parallel to the polarizing light. Parallel to the polarization of the electric field of the exciting light. Again, we're not going to want to talk too many details in treating this slide, but the bottom line is that's because the efficiency of excitation is proportional to the dot product of the electric field vector of the exciting light in the transition dipole moment. So the transition dipole moments that are aligned with the with the polarization of the exciting light will have a high dot product, and those that are perpendicular will have a zero dot product, and so there'll be preferential excitation of the fluorophores aligned with their transition dipole moments parallel to that of the exciting light, the electric field in the exciting light. Now, if this emission process occurred without a change in the location, if the emission process occurred without a change in the orientation of the fluorophores, if the polarization of the emitted light would, of course, be biased in the same way as the polarization of the exciting electromagnetic field. It wouldn't actually be identical for reasons we'll talk about later on. There's something called photoselection. I'll sort of mention it, describe it in a very simplistic way in a moment, and then treat it in a bit more detail later on. If there's no reorientation of the fluorophores that are excited, you will retain significant polarization from the because the excitation will be biased towards the fluorophores that are aligned with the incoming with the polarization of the exciting light. If there's no reorientation, the emission will be biased in the same way. However, because there's a time lag between the absorption and the emission, in a solution there will be rotational diffusion. That rotational diffusion will occur at a varying rate, depending on the size of the molecule, depending on the temperature of the solution, depending on the viscosity of the solution. We'll look at that in a moment. We'll summarize those points more carefully in a moment. But the bottom line is, because of that time delay between excitation and emission, because rotational reorientation can take place during that time period, the anisotropy, the input polarization tends to be scrambled as the fluorophores rotate. Later on, we'll look at a more quantitative treatment of that. In this screencast, we'll talk about that in a bit more detail, but still not derive it. In later screencasts, I will go through the step-by-step derivations. For now, the important point is that if you have enough rotational diffusion, you'll totally scramble these orientations. And then you will end up with basically unpolarized emission. And so that depending on the amount of rotational reorientation, you can go from either preserving a large fraction of the input polarization or totally losing the input polarization. So this is a qualitative overview of the phenomenon. And so then to step through the key points you want to make sure you understand and remember. Fluorescence anisotropy measures relative polarization of emitted fluorescence versus exciting light. So again, quantitatively, anisotropy is defined as the intensity emitted parallel to the polarization of the exciting light minus the intensity emitted perpendicular to that over the sum of the parallel intensity and 2 times the perpendicular intensity. I'll explain that factor of 2 weighting later on. Okay, so anisotropy declines with increasing rotational scrambling of fluorophore orientation during the time between absorption and emission, right? More rotation between absorption and emission, more scrambling or loss of fluorescence. So this is sort of a foreshadowing a point of nomenclature, a technical point. So the anisotropy declines with decreasing rotational correlation time. Rotational correlation time measures how long the orientation rotational correlation time is basically the time constant for loss of orientation or scrambling of orientation. So we'll see that the rotational correlation time is the time it takes for the net orientation to go down to a value of 1 over E of its initial orientation. And so Again, rotational correlation time is a quantitative measure of rotational diffusion rate. Long rotational correlation times means the, sort of the memory of the orientation is retained for a long period of time. Low rotational correlation time means the memory of the polarization of the orientation is lost much more rapidly because there is much more rapidly reorientation. So long rotational correlation time, slow rotation, low rotational correlation time, fast rotation. With fast rotation and low rotational correlation time, more serious decline in anisotropy. Okay, so again, anisotropy declines with increasing rotational scrambling, which corresponds to decreasing rotational correlation time. Okay, so you have to understand the physical point, and you should know the nomenclature roughly. We'll talk about this in more detail in a bit, but roughly what is rotational correlation time? So because of this, anisotropy generally increases with increasing molecular volume or size. Why? Because when molecular volume and size goes up, rotation rate of macromolecules is determined primarily by the viscous interaction of their surfaces with the solvent. Bigger things have more surface area. Bigger things, therefore, because there's more viscous, more basically frictional drag on their rotation, they rotate more slowly. So big things rotate more slowly. That means they retain memory, as it were, of the input polarization for a longer period of time, and therefore anisotropy generally increases with increasing molecular volume or size. Anisotropy also increases with increasing solvent viscosity or decreasing temperature, because both of these things slow molecular rotation rate. Right? If the solution is more viscous, there's more frictional drag. If the temperature is lower, there's less thermal energy. With less thermal energy, things rotate more slowly. So anything that slows down the rotation, increasing molecular size, decreasing temperature, increasing viscosity, anything that slows down rotation increases anisotropy. We'll look at that in a bit more detail later on, but still qualitatively in this presentation, and then we'll look at the quantitative. We'll look at the equations more carefully in a subsequent presentation. So now this is a tremendously important point. It would be hard to derive it because it involves some slightly not terribly advanced, but advanced enough math that we'd have to spend a whole class just looking through the math. So I'm just going to state the result, and you're just going to have to believe it. The most important thing is you understand its importance. The measured values of anisotropy are linearly proportional to fractional occupancy of molecular states with different values of anisotropy, which makes it convenient for quantitative analysis of binding experiments producing a significant change in rotation. Right? So if you have, as we saw in some of the papers that we reviewed in the discussion sections, if you have, let's say, a smaller molecular species, for instance, a nucleotide that is fluorescent, and small species rotates rapidly, will have low anisotropy. If it binds to something large, that will then rotate more slowly. It will have higher anisotropy. The measured value of anisotropy from a solution containing a mixture of species in two different states will be linearly proportional to the fractional population in the two states. So in other words, if it's all in the small state, you'll get the anisotropy characteristics of the small state. If it's all in the large state or bound state, you'll get the anisotropy characteristics of the bound state. If it's 50-50, you'll get an anisotropy 50% between those two values. If it's 75% in the large state, you'll get a value 75% between those two values, and 25% in the large state, 25% the two values, right? So there is a linear proportionality between the anisotropy as it progresses between the limiting values and the fractional occupancy of the molecular states. That may sound trivial. It's not. It's actually wrapped up into the mathematical characteristics of this slightly complicated way of analyzing the polarization of the emitted light. Okay, so final overview point. Photo selection limits maximum anisotropy to 0.4 for molecules with parallel absorption emission transition dipole moments. So basically, the excitation process, of course, is the efficiency of excitation is proportional to the square of the dot product of the electric field vector with the transition dipole moment vector. So obviously there's preferential excitation of things that are aligned parallel to the excitation vector. On the other hand, it depends on the dot product. That dot product is only 0 if the things are oriented perpendicular to the excitation vector. So as you go from a perpendicular orientation to a parallel orientation, you go from no excitation to the most efficient excitation, but things in the middle, things with orientations between perpendicular and parallel, will be excited to a varying extent. And so we got to do basically some multidimensional calculus to figure out exactly what that value is going to be. Once the fluorescence is emitted, the polarization of the emitted light will match essentially the orientation of the transition dipole moment for the emission. Now, if you have a single electronic transition involved, for the transition dipole moment is, again, more or less the difference in the dipole moment between the excited and the ground state. If the fluorescence process involves a single electronic transition, it has to have the same transition dipole moment for the absorption process and the emission process. In some cases, you can actually have excitations into higher electronic quantum states that then decay by internal conversion to lower ones. So there are some cases where there is an angular offset between the transition dipole moment that's responsible for some or all of the absorption and the transition dipole moment responsible for the emission. In that case, this photo selection rule becomes a bit more complicated. But in most cases, you're looking at primarily, dominantly, a single electronic state undergoing either excitation or emission. In that case, the transition dipole moments are physically the same thing, and therefore they're parallel. When the transition dipole moments for absorption and emission are parallel, the highest possible anisotropy is 0.4. And that's, again, because though there's the most efficient excitation of the things that are absolutely parallel to the polarization of the input light, the excitation is only 0 when they're perfectly perpendicular, and so there is a increasing efficiency of excitation as things go from perpendicular to parallel. And when you do all the proper integrations, and then you calculate properly the polarization, the anisotropy rather, of the output light, it turns out that for the simple case of parallel alignment of the excitation and emission transition dipoles, the maximum possible anisotropy is 0.4. Again, that's because something at a 45-degree angle to the excitation vector will be excited to some extent, not as much as the parallel ones, but excited to some extent. And when it's excited to some extent, it will emit. It will then emit, if it doesn't rotate at all, it will emit a characteristic of the transition dipole moment at that 45-degree angle, and that will already have lost some of the polarization. So for that reason, the maximum polarization you can get due to the photoselection process is 0.4, again, unless you have some difference in the angular, unless you have a non-parallel alignment of absorption and emission transition dipole moments, which is not unheard of, but is rare. So in general, 0.4 should be the maximum value you see for anisotropy. One more comment before we move on. Polarization is a different mathematical function of the parallel and perpendicular emission intensities. Basically, polarization is the evil twin of anisotropy. This is a measure that, sort of in some simplistic analysis makes sense. The difference between the intensity and the two polarizations divided by their sum. Simplistically, this makes sense. In terms of a rigorous mathematical analysis, it does not. Polarization, basically, in my opinion, should just be ignored. Anisotropy has the proper mathematical behavior. Again, critically, it is the anisotropy values will be linearly proportional to fractional occupancy of molecular states with different values of anisotropy. And so it's population proportional. It's linearly proportional to population. That makes it the measure you want to use, because typically in biophysics you want to know what fraction of your population is in which state, bound versus unbound, and therefore anisotropy is the numerically most effective and convenient variable. Okay, so that is those are all the big points. If you remember nothing more than that, you're still going to be in at least have a reasonable sort of qualitative understanding and memory of what's important about fluorescence anisotropy. So let's go on to the next slide and start digging through some of this material a little bit more deeply and looking at it a bit more closely. So only I want to go through the math in detail, but 2 points. The anisotropy is going to be, so what we're going to do is we're going to excite light with excite fluorophores with linearly polarized light. Typically, we do this in something called a T-format fluorimeter. In this case, the exciting light wave is vertical, as oriented here in this schematic. The vertical light comes in and excites the fluorophore. Then we measure the emitted light with 2 different polarizations, right? So what we do is basically we have a polarizer come on the excitation side that makes sure that the light coming in is linearly polarized in this direction. Then we have polarizers on the emission channels that select exclusively light with this polarization or exclusively light with that polarization. We call the light with this polarization the parallel polarized light because its polarization is parallel to the excitation direction. We call light coming out with this orientation perpendicular polarization because its polarization is perpendicular to the direction of the exciting light. So the anisotropy is defined as the difference between the intensity emitted with parallel polarization minus the intensity emitted with perpendicular polarization over the intensity with parallel polarization plus 2 times the intensity with perpendicular polarization. Well, where does that 2 come from? Well, if you think about it, right, so when the excitation process has taken place, slightly oversimplified, but to a first approximation, we have excited transition dipole moments with this orientation. Right, so then the emission, if it emits, like let's say it emits before it's rotated at all, it would retain exactly that same polarization, and it would give us the parallel polarized light. But when it rotates, actually, when this dipole rotates, it can rotate either sort of so that it points along this direction, right? So now if we look for a rotation of 90 degrees, a 90-degree rotated dipole can point either in this direction, in which case actually the light emission would be coming out to either side, or it can rotate down to this direction. Right, this direction is effectively parallel to this I perpendicular vector. So basically, if we want to look at where the transition dipole moments can be, we have one transition dipole moment. Well, the transition dipole moment can retain its parallel alignment with the exciting light, and that gives us the parallel emission. But when we've rotated 90 degrees out of plane, there's sort of 2 different directions there, right? There's this direction, the transition dipole moment, which emits the perpendicularly polarized light that we can see. There's a second direction in the perpendicular orientation that actually emits light in this direction. We can't see the light in this direction, right? Even if we put a detector up here, we would be seeing the combination of the exciting light that hasn't been absorbed in the emitted light. So basically, light emitted from dipoles with this orientation is just lost, but by symmetry, it has to be equivalent to the amount of light emitted with this orientation. Okay, and so that is why to get the total amount of fluorescence emitted, we take 2 times that quantity because it accounts for this component of the fluorescent light that we can't measure, and then we sum it with 1 times that quantity. And so this summation, the parallel polarized intensity in the parallel direction and 2 times the intensity in the vertical direction, that gives us the total. Sorry, still haven't really quite mastered the art of writing on this pad, but this gives us the total fluorescence. The anisotropy is the difference between the parallel and polarized intensities divided by the total fluorescence. Sorry, that's a bit ugly. That's supposed to say total. Okay, now an important point here is that the anisotropy behaves according to something called the second-order Legendre polynomial of the orientational distribution. Let's not worry about what this is, but let's just focus on the point that this second-order Legendre polynomial essentially is averaged over the ensemble of orientations in the molecules, right? So what happens is once we excite the molecules, the rotational diffusion is a stochastic process. They'll all have rotated to a somewhat different extent. So by the time the emission happens, we will have an ensemble of molecules with different orientations of their transition dipole moments. The important point about this Legendre polynomial is it is averaged over the population. And so basically, the relative contribution of any subpopulation will scale with the size of that population, right? So basically, it's a populated way. So in the end, this Legendre polynomial math gives you a population-rated average over the species, states, and the distribution. So I'll read this. The most important point here is that this function is an arithmetic average over the population. So for a mixed population, the observed steady-state anisotropy is the population-rated average of the anisotropy of each individual state or species. Given fractional populations f of n, the observed anisotropy would be the fraction of the population in any given anisotropy state times the anisotropy of that state. So basically, what does this mean, right? So we're saying the observed anisotropy is the sum over the anisotropy of the individual states scaled by the fraction in that state. What this means is that anisotropy values scale linearly with population. There's a linear relationship between the anisotropy and the population of any given state. So the important point here is the linearity in fractional population. Because it's linear in fractional population, we can use anisotropy to tell the relative amount of in a mixed population, we can tell the relative amount in one state versus the other state by looking, right? The relative amount in one state compared to the other state, the anisotropy will move linearly between the anisotropy in each of the individual states. So let's pause and think about that for one moment. Suppose we have everything in one state. Then we will say we have state 1. So let's call that R1. So if you have a population entirely in state 1, which has anisotropy R1, we will observe R1 anisotropy. Suppose we have another state of the system, like the bound state, right? We looked at, and in the papers we looked at, the research papers, anisotropy was used to measure binding. Smaller things binding to larger things slow down. Larger anisotropy in the, smaller anisotropy in the free state, we could say R1 went to larger anisotropy in the bound state, right? So let's say we have an entirely free population, it has anisotropy R1. Let's say we have an entirely bound population, we'll have anisotropy R2. What this says is that the fractional, we'll say the observed anisotropy value will follow directly the fraction of the population in each state. So what this means is as we go from the completely unbound population with anisotropy R1 to the completely bound population R2, the amount that's bound versus free will scale linearly with the relative value of anisotropy in this window. Right? So if we take a value of anisotropy that's, let's say we have a value of anisotropy midway between R1 and R2. Let's say we have a population with half of it in the R1 state, half in the R2 state. What this says is we will get the arithmetic mean of those two anisotropies. The anisotropy will scale linearly with the fraction of the population in each of the states. So for two-state phenomenon, we can just look at the relative value of the anisotropy relative to the limiting values of the anisotropy, and that will give us the fractional representation in the fraction of the population in one state versus the other. So hopefully that's clear. I'm happy to discuss that further if it's not clear. And so down here, all this is supposed to schematize is that the transition dipole moments have fixed orientations within the molecule, right? They're fixed because the dipole moment is well defined. The dipole moment looks at the first moment of the charge distribution. The transition dipole moment is the difference between the first moment of the charge distribution and the excited state compared to the ground state. That will have a well-defined magnitude and orientation within the molecule. Actually, in general, the emission transition dipole moment will be collinear with the absorption dipole moment. In general, excitations will happen, emissions will happen between the same kind of quantum states as the absorption happens. If there's an internal conversion process, however, let's say changing the molecule between two different electronic excited states, right? We saw earlier that you can actually have an electronic transition into a different electronic excited state. By internal conversion, that can decay to the electronic ground state. The different electronic excited state might have a different transition dipole moment. Well, a different electronic excited state will have a different charge distribution. It's therefore likely to have a different dipole moment. It's therefore likely to have a different transition dipole moment. If you then decay into a ground, if you decay into a lower electronic excited state, that again could have a different transition dipole moment. And so there can be, for a given, for the movement between two given electronic quantum states, the emission and the absorption dipole moments are always going to be collinear. It's just the difference in the dipole moment given by the charge distribution. But because internal conversion can move molecules between different excited states before they fluoresce, there can be an offset in the orientation of the so-called absorption transition dipole moment and the emission transition dipole moment. This is a bit of a geeky point. It is worth bearing in mind, however, that these things do not have to be collinear because of that complexity. But the important point in anisotropy is that when you excite a fluorescent population with a given polarization of light, you will preferentially excite molecules with their transition dipole moments aligned with the exciting polarization of the exciting electric field vector. And then what makes anisotropy interesting is that the time delay between the emission and the, between the absorption and the emission. Because there's a time delay, the molecule will reorient during that time. When it reorients, the polarization of the emitted light will change. We use this setup that I just described to measure that polarization change quantitatively. There's math that I won't bother going through in detail. Won't go through it all today. We'll never lead you through all the nitty-gritty of this, but there's math that ends up, the math shows that this way of quantifying the anisotropy, or the difference in polarization, is most useful. Why is it most useful? It's most useful because this quantity scales with the fractional population of states with different individual anisotropies. And so basically, the anisotropy is going to be linearly proportional to the amount of the population in a given state. And that's the important point about anisotropy. That's why we use anisotropy as the basis of our observations and quantification of state occupancy. Okay, so this presentation has gone on very, very, very long. I don't want to cover too much more today. I just want to summarize a couple, again, qualitative points. We're not going to look at the math at all. But I just want to make the point that when an individual fluorophore is excited, it happens on the femtosecond timescales we said before. Actually, it is possibly experimentally, physicists have designed lasers that actually can produce a light pulse on the scale of a few femtoseconds. And so these femtosecond laser pulses actually can be used to excite a fluorescent population. Actually, Columbia, we don't have one of these instruments, but we should. They're not particularly expensive. Just reflects Columbia's lame support for science. But for about $100,000, you can buy an instrument that will actually produce a femtosecond timescale pulse of light. And then you can, if it's strong enough, you can excite a lot of fluorophores very quickly over the times on that femtosecond timescale. And then you can have electronic instrumentation that will actually look at the fluorescence and the anisotropy of the fluorescence on that on the nanosecond timescale. And so, again, for about $100,000, you can buy an instrument that does this. And so this is just schematizing what happens after such a pulsed excitation. And so this is a way to look at kinetically what's happening to a population that, let's say, starts off with uniform excitation. And so here we're showing the instantaneous relative fluorescence, right? So again, this experiment can pretty easily be done. You shine a femtosecond duration laser pulse on a cuvette containing a fluorophore, and now the fluorophores can be driven, especially if it's an intense laser, you can drive a lot of fluorophores into the excited state, and now you can watch how they fluoresce, and you can watch the anisotropy of that fluorescence. The solid and the dotted line here are supposed to show fluorophores with two different lifetimes. We're going to talk about lifetime quantitatively later, but the lifetime is defined as the time it takes the fluorescence to k to 1 over e of its original value. We'll worry about the math later on. So this is a fluorophore with a shorter lifetime. This is a fluorophore with a longer lifetime. If the fluorophore has a shorter lifetime, the fluorescence intensity decays more rapidly. If it has a longer lifetime, the fluorescence intensity decays more slowly. So this is the fluorescence lifetime. This is basically the time scale of the emission. It's related to the quantum yield of the fluorophore. We'll come back to the detailed math later on. Now, separately from the fluorescence lifetime, there is a rotational diffusion lifetime. This is something called the rotational diffusion coefficient. Now, the anisotropy, the instantaneous anisotropy, is determined by the rotational diffusion. If a small molecule has a fast rotational diffusion, the anisotropy decays more rapidly. A slow molecule has a slower rotational diffusion. The anisotropy decays much more slowly. Now, we could have either a low lifetime fluorophore or a high lifetime fluorophore on a molecule that has either fast rotational diffusion or slow rotational diffusion, right? So basically, these are independent physical properties. The steady state anisotropy that we see is going to reflect the time averaged value of the anisotropy over the course of the fluorescence emission. So, so the fluorescence is falling off at a certain rate. If we want to know, if we're looking at the so-called steady state anisotropy, in most experiments we would be just continuously exciting the whole population and looking at effectively in most experiments we will continuously excite the population and look at the average value of anisotropy. In this experiment, we excited the population with at a very discrete point in time, and then we looked after that pulsed excitation at the properties of the ensemble that were excited in that very short period of time. In bulk fluorescence measurements, however, what we're typically doing is continuously exciting the population, and then we're looking at the time averaged anisotropy. How do we get that time averaged anisotropy? Well, what that would reflect is the average anisotropy weighted by the amount of fluorescence emission each time, right? So the fluorescence, so let's say we have something rotating rapidly. It follows this rotational decay curve for the anisotropy. And we have a fluorophore with a relatively short lifetime. So at this moment, the fluorescence that's being emitted would have this anisotropy. By the time we get out here, the fluorescence that was being emitted would have zero anisotropy, right? Because the anisotropy has decayed more rapidly than the fluorescence has decayed. Conversely, we could take a molecule with a longer fluorescence lifetime and look at what happens to the steady state anisotropy there, right? That would have a different weighting of the anisotropy, right? So what we're going to, when we do a steady state measurement, we're looking at basically the average anisotropy produced by this decay process. Any given molecule will absorb light on the femtosecond time scale. We can produce a whole population that absorbs on the femtosecond time scale, but even when we're doing continuous excitation, a given molecule will absorb on the femtosecond time scale. So for even when we're doing continuous excitation, these decay curves will describe the probability function of the rotational of the anisotropy and of the fluorescence emission, right? So for a given molecule, this basically describes the probability that it will decay at a given time relative to the absorption event, right? That's what, when we excite the whole population instantaneously at this time, it's made of individual molecules. And so, we excite everything at this moment, and then one by one they are decaying. This curve describes the probability, right, for decay over time. So we can set this up experimentally so that we can observe that. And again, people do this. It's interesting and useful. But when we do a continuous experiment on a bulk sample, even though we're continuously exciting the fluorophores, each individual fluorophore will follow this same sort of probability, these same probability curves. To get the mean anisotropy that we observe, right, which we call the steady state anisotropy, to get the steady state anisotropy that we observe, we'll have to find the expectation of the value of the anisotropy given this time scale of the emission. And to do that, we need to evaluate some integrals. So I'm not going to do that today. I'll do that in a screencast focused simply on the evaluation of those integrals. Okay, now the last thing we need to understand about anisotropy is something called photoselection. What we saw early on or sort of to some extent our starting point for this adventure in spectroscopy, was looking at the fact that the probability of exciting, the probability of the electric field component of light transferring energy to a molecule is proportional to the dot product of the electric field vector with the transition dipole moment vector, or the change in the dipole moment in the course of the transition. It's proportional to that dot product squared. Right? So the dot product will depend on the magnitude of the electric field, the magnitude of the transition dipole moment, and then their mutual orientation. And that orientation component is given by the cosine of the angle between the electric field and the transition dipole moment. Right? And so then the square of that cosine term will describe the probability of the excitation. To understand what happens in an anisotropy experiment, we have to understand the probability of excitation now as a function of the orientation of the molecule. And that's what this is all getting at here. And this is describing a property called photoselection. If we take a solution of molecules, right, they're going to have a random orientation, and therefore their transition dipole moments will have a random orientation. So if we say we take, suppose this is sort of our conceptual cuvette here, and say we do an experiment with the, where we excite the fluorophores in this cuvette with the electric field of light polarized in this direction. In the cuvette, the molecules will have all random orientations relative to this electric field vector. And that means their transition dipole moments will have a random distribution relative to this electric field vector. If the transition dipole moment is perfectly aligned, right, this cosine term will be 1, and we will get the most efficient excitation. If their transition dipole moment is orthogonal to the electric field, this dot product, this cosine term will be 0 at 90 degrees, and we will get no excitation. For orientations between 90 degrees and 0, we will get a varying degree of excitation. To figure out exactly how much excitation we're getting for a fluorophore with a given orientation, we will have to do some integration. We will have to integrate over these two probability distributions. I'm not going to do that now. It's relatively simple multivariable calculus. I will do it for you in another screencast. The bottom line is when you do this excitation, well, we have to first figure out the probability of the excitation, but then also we have to look at the probability of the emission, right? The anisotropy is depending on the probability of the emission. The anisotropy depends on where the emission takes place compared to the excitation. As I told you before, the anisotropy is given by something called a Legendre polynomial. The Legendre polynomial is basically a function of the angle between in this case, the transition dipole moment and our exciting electric field vector. And so if we know the distribution of the transition dipole moment orientations, basically we can directly calculate the steady state anisotropy. We can calculate the expectation value of the anisotropy if we know the distribution of the orientations of the transition dipole moments, right? And so it turns out the reason we use the anisotropy is because this Legendre polynomial math is very simple. It would be a bit harder to explain to you where the Legendre polynomial math comes from, but for the moment, let's just accept the Legendre polynomial as giving a very, very simple functional form for the anisotropy that you expect from a population with a given distribution of transition dipole moment orientations. And so, again, it's a very simple cosine function of the distribution of transition dipole moment orientations. And so, effectively what this enables us to do now is we can look at the efficiency of the excitation as a function of transition dipole moment orientation and then the distribution of transition dipole moment orientations that you have in a randomly oriented sample. And we can sort of plug that into an ensemble average in this Legendre polynomial expression. And from that, we can calculate the expectation value for the anisotropy at time 0. So what we can do is we can now conceptually sort of freeze the solution. conceptually freezing the solution is equivalent to what happens in the first sort of few femtoseconds after the initial absorption event, right? Femtosecond time scale is too small, it's too short for molecules to reorient. If we look at the anisotropy of the fluorescence emission in the first few femtoseconds after absorption in a femtosecond excitation experiment, it is basically equivalent to looking at the emission in a frozen solution. So you could actually do this two ways. You can do a femtosecond pulse experiment, or you can actually literally freeze a solution of fluorophores and get rid of the kinetic motion and then just sort of trap the orientational distribution in time. When we do that either way, we see that this photo selection process, the variable efficiency of excitation depending on the angle of the fluorophore compared to the electric field. For a fluorescent molecule population with a random orientation, we can show that that variable efficiency of excitation gives us an initial anisotropy of 0.4. And so that's an important number because we need to, if you want to do fluorescence anisotropy, you've got to know that number. You've got to understand that that's the maximum physically realistic value. This derivation does assume that the transition dipole moment for excitation and emission are parallel to one another. Again, that's not always the case, but it is usually the case. Only with very special fluorophores do you get an initial anisotropy more than 0.4. So that's an important number to know. Most of our fluorophores do have excitation and emission transition dipole moments perfectly aligned because most of them were looking at a transition into and out of the lowest energy electronic excited state. In that case, they have to be aligned. And so for most fluorophores, the maximum anisotropy you can get is 0.4. So this slide shows some interesting properties now of anisotropy. What we're doing is we're plotting reciprocal anisotropy. Why? Because we can use something called the Stokes-Einstein relationship to figure out how we expect the rotational diffusion rate of a particle to vary depending on its size. And so what effectively this enables us to do, this Stokes-Einstein relationship enables us to predict the rotational diffusion coefficient for a molecule from its molecular weight, assuming it has a spherical shape. I'm not going to go through the details now. Let's just go back over here. The key point is that the molecule has a certain rotational diffusion constant. Again, the really convenient mathematical property of the anisotropy. These Legendre polynomials, without trying to derive how you get them, their convenient property is that they produce a population weighted average when you have a mixed population. Their other incredibly convenient property is that you can describe the rotational, you can actually describe decay, right? You can describe the rate of decay of the anisotropy by an exponential by a simple single exponential term related to the rotational diffusion coefficient, something called the rotational diffusion coefficient, right? So this rotational diffusion coefficient reflects the rate of rotational diffusional reorientation. The anisotropy value is dependent in a simple exponential way on the rotational, the anisotropy decays as a single exponential in this rotational diffusion coefficient. The reason the anisotropy decays that way is that the anisotropy, those Legendre polynomials, behave as a population weighted ensemble average, over the different anisotropy states in the solution. Because of that, effectively, it's probably hard to follow these details, but the bottom line is the anisotropy decay rate is described as a single exponential in the rotational diffusion coefficient. That's probably the simplest way to say it. The decay rate of the anisotropy with time follows a simple exponential in the simple single exponential in the rotational correlation time. This has to do with the mathematical. This ultimately comes from the fact that the Legendre polynomial that describes the anisotropy gives a population-weighted fraction, a linearly weighted average over the population. Because the anisotropy reflects a linearly weighted average over the population, you can put that together with the physics describing rotational diffusion, and you will see that the anisotropy decays as a single exponential with a lifetime given by the rotational diffusion coefficient, right? So basically what this Stokes-Einstein relationship enables you to do is to estimate the rotational diffusion coefficient from the molecular weight. The bottom line is, as I told you earlier, larger molecular weights, longer rotational correlation coefficients, right? So let's go back one more time. The rotational correlation coefficient is effectively how long it takes the anisotropy to decay to 1 over e. That means bigger objects, slower rotations, longer rotational diffusion coefficients, right? So bigger molecules, longer rotational diffusion coefficients. Rotational scrambling or reorientation of the molecule takes longer. The equation derived in the previous slide, which I will not go through mathematically now, but I will go through eventually, enables you to calculate the steady state anisotropy as a function of the initial anisotropy from photo selection and the fluorescence lifetime and the rotational diffusion coefficient. So basically, knowing the fluorescence lifetime, right? We can know the fluorescence lifetime from a pulsed nanosecond excitation experiment of this time. We can know the rotational diffusion coefficient in a number of ways. We can actually estimate it for a sphere just from the molecular weight. When we know that and we know the photo selection initial anisotropy, we actually can predict the steady state anisotropy in a population. Again, I'm going to go through the math of this with you in another screencast. But the bottom line is, the rotational diffusion rate will depend on the rotational diffusion. The rotational correlation coefficient depends on the molecular weight, but it also depends on viscosity and temperature. Eta here is viscosity. You probably have a qualitative feeling for what viscosity is. Something that's viscous, it's harder to move through it. Something that's viscous, a solution that's more viscous has more resistance to motion of materials in it. The viscosity, therefore, will tend to impede the rotation, right? Sticky, viscous solutions tend to impede movement. Viscous solutions, therefore, tend to slow rotation. More viscosity, longer rotational correlation time because there's slower rotation. Higher mass, longer rotational correlation time because there's a slower rotation. Temperature, on the other hand, speeds up motion, right? As temperature increases, energy, as we saw earlier, goes into all of the so-called thermodynamic modes. Of course, the motion represent very important modes, very important places that energy is stored in solutions. When you increase temperature, there is more motional energy. Motion is faster. As motion gets faster, things rotate more rapidly. As they rotate more rapidly, the rotational correlation coefficient goes down because there is faster rotation. So with these simple quantitative relationships, you can put a bunch of things together. We can, again, from the fluorescence lifetime, measured from a pulsed nanosecond experiment, from the rotational correlation time, estimated, let's say, from the Stokes relationship, we can get in from the initial photoselection excitation, we can determine the steady state anisotropy that you would measure from a population that's under a continuous excitation condition. Again, I'll go through the math of this in a different presentation. What we want to think about now is the fact that the steady state anisotropy depends on these interesting molecular properties: fluorescence lifetime, molecular mass, viscosity, right? And so these things all fit together. Now, the functional form of this is such that if we rearrange this, we can show that the reciprocal of the steady state anisotropy should depend on, in a rather simple way, on variables that are sort of interesting to know about and that we care about. The fluorescence lifetime being one of them, but then the molecular weight and the viscosity. And so what this says is that a plot of reciprocal steady state anisotropy versus, let's say, T, or T over eta, should be proportional to fluorescence lifetime in molecular weight, and then something called partial specific volume. I'll talk about this later on. That's basically what you need to go from molecular weight to surface area to volume. You need partial specific volume to go from molecular weight to surface to molecular volume. The rotation rate depends on the molecular volume, and so this is getting you basically molecular volume. So if we plot now reciprocal anisotropy versus temperature, absolute temperature over eta, viscosity, we get something called a parent plot. And this is quite interesting. So as we increase temperature, things rotate more rapidly. As we increase viscosity, things rotate more slowly. That means as we decrease velocity, things rotate more rapidly. So increasing temperature, of course, increases this quantity. Decreasing viscosity increases this quantity. So you have this sort of interesting ratio of temperature to viscosity. And what this relationship here, the parent plot, shows is that you expect reciprocal anisotropy to go linearly with the ratio of temperature to viscosity. So what this means is that we can use anisotropy to measure basically molecular weight. We would use it to measure molecular size. What we would get from, right, what is the slope of this line here? This equation tells you the slope of this line is fluorescence lifetime times R, the ideal gas constant, a constant, over R0, the photoselection anisotropy, times the volume of the, that's actually the hydrated volume of the particle. Mass times V bar plus H gives you the hydrated volume of the molecule. I'll come back to that later on. But so basically, this means if you know this slope, you should be able to measure the hydrated volume of the molecule. And so this is quite useful way to characterize molecules, to know the hydrated volume. So what we do then is we measure anisotropy as a function of either increasing temperature, or we can increase the viscosity if you put glycerol, right? And there are other things that make solutions sticky and more viscous. So we can experimentally manipulate the viscosity or change the temperature. When we increase temperature or reduce viscosity, we should get a linear change in the reciprocal anisotropy. From the slope of that, we can learn the hydrated molecular volume. That's quite important. Now, when you go to what's going on here, down here we're going to zero temperature or infinite viscosity. Zero temperature or infinite viscosity, that's probably too much at once. Zero temperature, infinite viscosity is basically freezing out all motion. If we freeze out all motion, we should see the anisotropy that reflects the photoselection process, which was derived in the last slide. If we freeze out all motion, anisotropy should reflect just photoselection, and so it should be 0.4 for a fluorophore that has its excitation and emission dipoles aligned. And so in some cases when you do, this is called a parent plot. In some cases when you measure experimental parent plots, you will see that. You will extrapolate back, and this will be 0.1 over 0.4 or 2.5. In other cases, interestingly, what you will see is you will get a parent plot. The slope of this parent plot should still reflect the hydrated molecular volume. But rather than extrapolating back to the photoselection anisotropy, it can extrapolate back to a smaller value. So, right, and so that means that our 1 over R0 is different from what we think it should be by photoselection. What explains that? Sorry. So, effectively, what's going on here is instead of having the actual photoselection anisotropy, effectively these equations are applying instead to an apparent photoselection, an apparent initial anisotropy. So what does this all mean? Well, when you go to zero temperature, infinite viscosity, basically you freeze out the motion. The parent plot is really looking at the rotational diffusion of the macromolecule. As you increase viscosity or decrease temperature, the macromolecule starts rotating more slowly. At this point, the macromolecule really stops rotating. What's happening when you have a larger reciprocal anisotropy means smaller anisotropy when you're freezing out all motion. That means there's some kind of segmental motion, right? This linear relationship describes the change in the rotational diffusion of a macromolecule. It turns out that when we attach a fluorophore to a molecule, it's usually done by some kind of flexible molecular linker. When solution viscosity increases, flexible things on the molecular scale do start moving a little bit more slowly, but for various somewhat complicated reasons. So segmental motion. Segmental motion means that some little chemical structure within this larger macromolecular complex is moving more rapidly than the overall rotation rate of the molecule, right? This Stokes relationship that we looked at earlier, right? The Stokes relationship looks at the overall molecular rotation rate, right? This Stokes term here looks at the overall rotational reorientation of the macromolecule. When we go to 0 on this T over eta, this letter is eta, the viscosity is represented by the variable eta. When T over eta goes to 0, we freeze out all of the macromolecular rotational motion. If 1 over R0 is too small, that means there's some motion that isn't frozen out. So what's going on here is, let's say we have a macromolecule, right? So we have some macromolecular species. I'm just going to make this some kind of, let's say this is some protein, some big protein that's moving rather slowly. When we put the fluorophore on the protein, it will tend to have, let's say that's some fluorescent species. The linking segment will tend to be flexible. That kind of flexible linker is not affected by viscosity in the same way. To a crude approximation, the flexibility, the rotational diffusion, so you can have basically rotational diffusion based on the flexibility of the linker. To a first approximation, that kind of rotational diffusion is not influenced by viscosity or not influenced anywhere near as much as the rotational reorientation of the macromolecule. So when you do this kind of experiment, effectively what you do is you're progressively freezing out the rotation of the macromolecule without much affecting the segmental or local motion of the fluorophore reorienting itself relative to the macromolecule. So when you do this kind of parent plot and you extrapolate to 0 temperature or 0 T over eta, effectively what you're doing is you're seeing what the anisotropy would be when the macromolecular rotation is stopped, but any other segmental motion that's in there is still going on. And so that segmental motion tends to be fast on the fluorescence time scale. And so basically whatever the segmental motion, whatever reorientation you can get out of the segmental motion has happened before any fluorescence has happened. You freeze out the macromolecular rotation, and the apparent initial anisotropy at that point reflects the segmental motion. Now, the math of those Legendre polynomials factors into this in a very neat way. You're actually, in this way, you are able to quantify the rotational diffusion coefficient for the segmental motion. We're not going to get into that, and that's more than I expect you to understand. But I would like you to understand that as you decrease temperature, increase viscosity, you slow down the molecular rotation. When you slow it all down, you should see the photoselection anisotropy described in the previous slide. If the anisotropy is lower than that, that means there's some reorientation even when you freeze out all of the macromolecular reorientation. That is affecting local segmental motion. And you can sort of dissect that from these kind of parent analyses. So this covers all of the qualitative things I want you to understand about fluorescence. There's obviously a lot of quantitative stuff in the background. I do suspect that the whole thing with the rotational correlation coefficient and the steady state anisotropy, the math might be so intricately weaved into that it's hard to sort of wrap your head around the qualitative parts of it. But I nonetheless think that's worth doing. It's worth trying to wrap your head around the qualitative things that I've just discussed, even if the math is a little murky. Wrap your head around the qualitative things I've just discussed, because this is what I want you to take away from this material, a year or 2 or 5 years down the line. And then I will come back to the math in separate screencasts. And then, hopefully by going through those, you can get a firmer grip and a deeper understanding of this. But the stuff that I really want you to understand and take away is the stuff that's gone through in this qualitative screencast.